I've known Dieter for about 25 years now, and
That's true.
Back 1,000 years ago, we tried to recruit him to the University of Texas at Austin and failed. He just showed up there after getting his PhD at the University of Bonn in Germany, and then I believe you were at a postdoc at Carnegie Mellon, is that correct?
Exactly.
Yes.
2 years.
So he went to the University of Washington, and things proceeded, and things have proceeded very well, as I understand. And so he is both a professor at the University of Washington, and he's running a major robotics group at Nvidia. And I will let him tell you all about it. Dieter.
Thank you very much. Thanks for inviting me over, and thanks everybody for coming. And it's also a great honor to be introduced by Ben, because a lot of his work was very inspirational to me, especially, I hope in your courses you're still teaching the spatial semantic hierarchy and things like that. It's especially now with visual navigation, it's becoming really relevant again, right? So pretty amazing. Yeah, so I want to share some thoughts I have on, these recent developments that we've been seeing and how they relate to robotics. So the title is Where's RobotGPT? Inspired by questions that I get asked a lot, and I'm sure many of the roboticists get this question asked a lot. And I'm gonna do this in the context of robot manipulation. So you've seen a lot of work related to locomotion kind of tasks, and here I wanna mainly focus on robot manipulation. And I guess we all agree actually that there have been astonishing developments in the area what we call generative AI over the last years, right? There is with these large language models, interactive language models, ChatGPT models, but also even generative models like Stable Diffusion that can generate beautiful images just being prompted by text. We can generate videos that look very realistic and also have some sense of even 3D consistency to them. And I think the main contributions that made this really possible are kind of threefold. So on the one hand side, all these models are trained on vast amounts of data, right? So language models are trained on, of course, internet scale data. Then also that the models themselves, right, these transformer models are actually amazingly large. And before that, whenever we in robotics, for example, did machine learning, it was always very small data and very small models. And here we see that these progresses that are being enabled, especially by just scaling everything 1,000-fold at least up, and then get these amazing results. And another contributor is, of course, that the kind of data that these models are trained on, especially also the language models, for example, is what from a robotics perspective you could call something like behavior cloning, where the idea is they are not trained on random collections of words, but they are trained on text that typically, let's say, humans put there, and they had some meaning in mind when they wrote this text. So it's not random text, but it's kind of text that has some understanding and some connection to it. And then you can just, if you think about this text as a 1D generation of words or tokens, then they're just trained based on a history of words to predict kind of what's coming next, right? So it's kind of like, again, cloning the behaviors of these people when they wrote their text, right? You're just trying to replicate that. And the key trick then is that if you do this on sufficient data, then these tasks that we ask them to perform later on turn into kind of in-distribution tasks, right? So you don't need to truly generalize beyond the training data anymore, because your training data virtually captures everything you want it to capture. I know there's various limitations. I'm sure many of you think about that the planning and reasoning is not quite as good and things like that, and I think we're all aware of that. But still, I hope that most of you agree that it is pretty amazing what these models can do, and nobody, maybe some, but virtually nobody was able to anticipate this of just a few years ago, that this would happen. So in robotics, of course, we haven't really seen this progress yet, right? And getting asked, like, okay, why haven't you achieved this, right? What's missing? Are you roboticists just not smart enough? And I think there's two main pieces there, right? On the one hand, it's what we call Moravec's paradox, which is this notion that the things that we humans believe that are really easy, such as picking up a bottle, and drinking from it turn out to be very, very difficult if you want to do that, for example, with a robot. And the things that we always thought are kind of the crown jewels of human thinking, playing chess or Go, that those turn out to be, I'm not saying easy, but much more doable for computers and for the kind of algorithms that we have. Right? So there's this misunderstanding of people, again, that these things like interacting with the real world are actually by far not as easy as we always think they are, just because we are not consciously actually reasoning about them. So I want to come from a perspective, let's say, glass half full, meaning that my current working hypothesis here is that if we could only generate robot data at very, very large scales, right, that also is of the nature that it's suitable for, let's say, behavior cloning. So it should be data that kind of demonstrates behavior that you want your robot to do. And if we combine it with these very, very large transformer-style models, then I believe that we could actually get to robots that are much more capable than the ones we have right now. This is, I'm not claiming that this will get us anywhere to true AGI or robots that really understand the world, but it's just kind of a practical thought where I said, like, okay, but at least our robots are going to get much better than they are right now. That's my hope, right? So I'm kind of like Ben, we're getting to the age where we are desperate and say we would like these robots to do something useful, right? No matter how. So this is not, I'm not claiming that this is the better approach than, for example, developmental work, especially the work, for example, inspired by people like Karen, who gave this wonderful talk in the morning. And I think these have to be combined ultimately, but for now, this is kind of the working assumption I'm making here. And then the questions are, of course, like, where do we get the training data from, and what should these models possibly then look like? And that's when I talk about. There's like 3 pieces. The first 2 are going to be on simulation-related data generation. But one thing that we are seeing right now in robot manipulation, especially with these developments in humanoid robots, is successful applications of behavior cloning, where people teleoperate the robots and they do certain tasks, and then we train these kind of often diffusion or transformer kind of models to replicate these tasks. And the demonstrations look, I think, extremely impressive often, right? One problem is people often tend to overgeneralize from these demonstrations, but still, it's showing at least the capabilities of these models. Now, one question is, of course, how do we scale that, right? So let's look at the different kinds of data sources that we have for training manipulation tasks. On the one hand side, you could say, well, we should just have our robots or our perception vision system watch videos, right? There are all these YouTube videos that show you how to cook. There are various efforts, especially driven by the computer vision community, on specialized data sets where they observe humans doing dexterous manipulation tasks, for example, the Ego 4D data set. My thought is on these data sets is that I think they're going to be very, very powerful on the long run, because they convey, of course, a lot of information. They can be used especially also for pre-training robot models because of diversity of the data that they contain. But at this point, there's still quite a gap between what we see in these videos and how you can transfer that to your real robot, right? Because we don't have the labels, for example, for the joint commands, and human interaction with these objects is quite different from what we see with these humanoid robots. Another source of data is teleoperation in the real world, which I just showed you some examples of on the previous slide. There have been various efforts in this, also multiple universities working together. Google DeepMind has been a key driver in that area with their ARM farm and other efforts. And I think, of course, this is super high quality training data, but at the same time, scaling this kind of data is going to be very, very difficult just because it's very expensive. Right? And the question is, who is going to have access to this kind of data to train their robots? And finally, one aspect I'm going to talk a bit more about is simulation, right? I think training robots in simulation can be very powerful because, of course, you can scale this arbitrarily. You can do things in parallel. You can generate many environments. But, of course, there's still the sim-to-real gap, which means you train a robot, it succeeds in simulation, but then it fails if you try to do the same thing with the same controller in the real world, and also open questions like where do we get all these assets from in order to train our robots in. So in this talk, I want to focus on the simulation and the benefits we're getting from that. Imagine just, and I give you just a few examples from the work we've done. Imagine you want to train a robot to grasp objects in simulation, and it turns out you can do this actually pretty easily. Let's assume you have here on the upper left, you have a certain object, right? That's a little can, but like and then you just randomly guess gripper positions relative to this object, okay? And then you feed that into your simulator, and you ask your simulator, if I take that gripper position and I'm going to close the gripper and then I'll shake it, will the object stay within the gripper or not? You see this here on the upper left, where some of these gripper poses are successful, while others, the object kind of just flies away. Okay? And the good thing is, in simulation, we can do this in parallel. We can kind of sample thousands and thousands of grasps and check out which of them are successful. And we can also do this for thousands of objects in simulation when we have the shape models. And what we're getting out of this is now a data set of objects, and they are all annotated with successful relative grasp positions. Okay? We can now take the data set and generate, for example, place these simulated objects on simulated tables. Okay, and then render simulated point clouds or observations, for example, and then just train a deep network, like a transformer network that operates, for example, on point clouds, to take in this observation and as output of the network generate where you should pick up this object. Okay, so the input is a point cloud, and the output is a successful grasp position, and this is supervised through this simulated training data. Does it make sense so far? Okay, and the nice thing is this transfers actually to the real world. So here's an example on the right side where we have a robot, and what you see in the upper row is, for example, we can present to the system an image of the object the robot should pick up, and then next to it you see kind of the scene, and in green you see the segmentation of the object that the robot will then pick up based on the target object. And then we use this network to output the grasp position for the gripper, and the robot can pick it up. What's interesting here for this example here is that all components of this are actually trained in simulation through learning, which means the grasp generation is trained in simulation, and also even the perception simulation that does the segmentation, things like that, we can also train in simulation. It's just by adding enough noise and randomization to the training data, these systems can become robust enough that they transfer to the real world. Here's just another example. And none of these objects were in the training data itself, but by training these models on, let's say, 10,000 different objects, they are not just memorizing these objects, but they're kind of learning the relationship between general shapes and successful grasps. Here's another thing that, for example, we can train. Imagine you want to teach a robot to where to place a book, for example, in such a bookshelf. So where is a free space, for instance, okay? We can do this by setting up a simulated shelf here, and we generate kind of point clouds for these objects. Pretty easy in simulation. And let's imagine for this blue object that you can see here, we know that this is where it should fit. And then what we can do is we can just add noise to that position. Okay? And you saw this, Guanya, for example, also mentioned that diffusion policies and things like that. So we first generate noisier versions of the position of this object, and then we can train a diffusion model, just like stable diffusion and these other techniques, to kind of reverse this process, where the network is trained to take a noisy position for an object and denoise it so that it fits into the free space in the shelf. Okay? And here's on the right side, you see an example for what this denoising then looks like, where these objects then all end up actually at pretty nice positions. Let me play this again. So we start with just random guesses for where the object should go, and then the network just figures out how to place them. And because it's trained on these point clouds, which we can also then train a network on, it actually works pretty well, zero shot in the real world. So this is now real world execution on these objects that were not explicitly in the data. It's not perfect, as you saw. It can't get them all right, but it demonstrates kind of just this notion of how we can, for example, here is a bit more complex placement task, but all of these can be trained purely in simulation. All right, so far these tasks were kind of relatively easy from a contact interaction point because it was just a grasping this object. It turns out for industrial assembly kind of tasks, there's what we call very contact-rich tasks, which means there's, for example, threading a nut onto a bolt or inserting. They have these tasks that are where it's very tight insertion of objects into a peg-in-hole kind of insertions. What you see on the left is kind of NIST developed this benchmark, and this is an older one. They now have newer ones that also involve kind of gears and also deformable objects, but this is one of the earlier ones. And that was used, you could actually order that and bring it to your lab and then use this to benchmark your robot's capabilities to insert these objects. And I always wondered why they need to do this with a physical object and why not just in simulation. It turns out I was just totally naive about it because simulating these kind of tasks is not as easy as you might think, because they have these very tight margins and you have to reason about the surfaces in a highly precise manner to simulate these kind of processes. So at the time when we looked at this, the kind of state of the art was something like that, where they were able to simulate this threading a nut onto a bolt. And again, this is not as easy as it looks because you have to really model all the contact surfaces between these two objects, right? And they have to be modeled very precisely. And from those then, you then get the friction and the torques and forces out of it. It turns out that simulation, it was kind of like a toy scale threading process, but the simulation was 350 times slower than real world. Okay, so which means a second would take 350 times longer, 350 seconds in simulation, and that kind of beats sometimes the purpose of doing simulation because we want to do things like reinforcement learning, and we need to be faster than real world. So we worked actually with Nvidia, with the physics team, which understands quite a bit about speeding up these kind of things, and they did some magical tricks. I can't go into the details here. They're in a paper, so it's not a secret, but it's just for the sake of time, but they use some representations like sine distance functions and also reducing of these contact surfaces. And based on this interaction, we were then able to simulate 1,000 of those in parallel, in real time, on a GPU. So again, beforehand it was 350 times slower, and now we can do real time, but with 1,000 in parallel. So here you can see such a simulation. Okay, and the nice thing is once you can simulate these things very fast, you can also start then training policies, right? You heard several talks already, reinforcement learning, so we can now apply reinforcement learning to these kind of tasks. So this was kind of the early work. And first, we were already super happy when we were able to train a policy that works in simulation, because it also shows, because if your simulator is actually not working well, then the policy will expose that. So the fact that we saw good policy rollouts made us pretty happy. But by now we're also able to transfer those things to the real world. So in the upper left you see simulated examples of assets, and right next to it are then real world rollouts. So we get zero-shot sim to real of policies that we train on these tight insertion tasks or threading tasks to the real world. We can also do policies now that use force feedback. Okay, so force torque sensing, and we can simulate the force torques and transfer those also to the real world. Interesting, let me speed this a little bit up. So it's putting in these different pieces, and then, let's see, towards the end here it's threading even a nut onto that bolt. So all of this is purely trained in simulation and then executed in the real world. One final example here is tactile simulation, tactile sensor. So these grippers have gel side sensors, so we can also simulate those and train policies that take tactile feedback into account and then execute those and execute them in the real world. He would just turn off the light to show that it's tactile. Yeah, sorry. Okay, but we're seeing some pretty promising sim to real in this. I'm not saying all of this is purely out of the box and it's fully solved, so there's still ongoing work, but I think these are very promising directions. And just one other example, I'm sure you've all seen this on more dynamics tasks where we can simulate this kind of reorientation tasks in a hand, in this case the Allegro hand. On the left side, it's done in simulation training. On the right side is then zero-shot execution in the real world, where we train both the perception and the control policy in sim. Okay, so this was hopefully kind of convince you a little bit that we can actually do the sim to real transfer for manipulation tasks as well. One question will be, of course, if we want to go to these very large models, is how we can scale that up. And I want to just briefly give you some idea of where we're going with this currently, also with respect to simulation. So there's different paradigms you can use to train your robot skills and policies in simulation. And we've seen some examples. For example, one is using reinforcement learning. Of course, the advantage of reinforcement learning is that it can learn like very complex policies. And you can also then, through distillation, for example, train them to work on perceptual data. We've seen several examples. And I think you mentioned the Eureka work, for example, is some line of work where you're using LLMs to generate reward functions or code for reward functions. So very promising work. But it's still, I think, at the level where this is not a truly, again, out-of-the-box experience. It's working for everything you would want to throw at your robot. So there's still quite some effort that has to be done on that line of data generation, let's say. Another idea is, of course, teleoperation. We see this actually, several data sets and environments out there use teleoperation to train, to control their robots in the simulator. But that has, of course, the same kind of a similar scaling issues and teleoperation in the real world, right? So it's kind of something that, if possible, I think we would like to avoid as much as possible just because it's very expensive and doesn't scale very well. Yet another way is do some automatic planning, and I'll talk a little bit about that, where we know, as roboticists, right, we know something about motion generation, things like that. So why do we need to learn everything from scratch? Maybe we can generate solutions in simulation, at least, using those existing techniques. And another ongoing thread right now, I think that we're seeing a lot of excitement also in the community, using these generative AI techniques like LLM, stable diffusion kind of techniques in order to generate, for example, to generate assets that you can put in the simulator. Then in your simulator, you ask your LLM, well, can you generate some tasks that the robot should execute? Then the LLM even generates steps for the solution of the task, and then you run reinforcement learning, for example, and out comes your trained policy. So this is kind of the hope for all of this. And because these LLMs have this kind of what we call open world reasoning, they scale to, and they can kind of invent new kind of tasks and environments. This is, of course, a very promising direction for scaling all of these efforts. The caveat at this point is that the assets, for example, that are being generated are not quite ready for physics simulation. And as we all know, the LLMs are also not quite as robust yet as we would like them to be. But again, I think this is a very promising direction to go into. Just briefly, how we could use planning, for example, in this context, is there's an area, robotics, we know about this, it's called task and motion planning, where the idea is, for example, you have your robot, you do planning both at a discrete level, about abstract actions, and where you model using logical predicates, you model preconditions of actions, you model effects of actions, and at the same time you then conditioned on these, you also plan, for example, continuous motion that the robot should do. So for example, if it wants to pick up a cup, it needs to actually be able to move the gripper to the cup and do so in a collision-free way. So there's a lot of work going on in this area. It's again called task and motion planning, and this is, for example, what such a solution could look like, and then we can execute that on the robot where it should pick up this teacup and put it on the stove or something like that. And there's still many improvements also on the motion generation itself, but the key idea is that we can do all of this in a fully automatic way. Right, all the planning. We just have to set up, of course, these kind of motion primitives and the predicates. We did some work, had this last year, how we could use this, for example, where then the overall idea is we first generate these simulated environments. You could imagine you just randomly generate whatever kitchens or something like that, and then we also generate tasks for the robot, and then we use task and motion planning to solve these tasks, right? And again, the key trick here is that the TAMP systems, they know how to solve these tasks in simulation. They wouldn't know how to solve them in the real world, because in the real world, many of the information that you need for the planning is just not readily available, right? In a simulator, I know exactly where every object is. In the simulator, I know the names of the objects. I know how to open a cabinet or the hinge points and things like that. In the real world, because of perception, I don't have that information. But here, since we're doing it in sim, they are actually very, very powerful. And then, let's say you run these solutions also through a physics simulator just to make sure that they actually work pretty well. And then you do this, what we call behavior cloning, because now what we have is, we have a set of tasks, and we have the motion that a robot generates to solve these tasks. And now we can do exactly the kind of behavior cloning that we see on the large vision and language models, right? Because we have all the kind of information that we need. And then we can execute it. And we did this with a transformer model last year again. The input then are these images, right, and the state of the robot and the task, and output is just the next control for the robot. And here's just some examples. These are the kind of tasks we trained then fully automatically in these large-scale simulation environments. But this is, again, also still just early steps in where we really need to go with this. One limitation here is really that with this task and motion planning, we cannot solve all the tasks, even in simulation. So, for example, if we look at this task here, that is one of the tasks that we see a lot in these demonstrations nowadays. Some of these steps require very context-rich reasoning, and task and motion planning can't automatically generate that. So you could imagine for some parts of these steps you would like to have teleoperation or reinforcement learning available in order to solve it. So what we can do here is, coming from a, let's say, planning perspective or TAMP perspective, we can set up the task and say certain aspects of these planning problems we know how to solve through motion generation and task and motion planning. And then there are certain steps in the task that the planner can't handle, and we just generate kind of human abstract actions where we say, well, that has to be solved by a human teleoperator, right? And the nice thing is, for these, let's say, teleoperated actions, we can still learn actually preconditions and effects so that we can incorporate them seamlessly into the planning process itself, right? And then during execution, for example, we can also switch between automatic generation of motion and the kind of policies that are trained through human teleoperation. So in this case, again, typically when you do these tasks, the things like inserting the pod into this little container, that is something that you would train from teleoperation. But how to move the object in free space to this location, that we can do through automatic planning. So let me just give you two examples here, what we can do then with just relatively few demonstrations. So it's about hanging this tool onto that hanger here. And again, in this case, certain parts of the task were generated through task and motion planning, and some sub-steps were actually controlled by a human teleoperator. And the planning system decided what happened when, okay? And it turns out that, of course, the advantage is that a human teleoperator only needs to work on the things that the robot can do automatically itself, right? So you can now, for example, have a single human teleoperator interacting with 100 or so simulated robots and just demonstrate the pieces that are necessary. So it's much more data efficient and time efficient. Here's another example. Of course, this also works then in the real world. And an interesting aspect here, just for you to notice, that we can, for example, as you saw, we can move the coffee machines and things like that around, right? In many of the demonstrations that we see nowadays, actually, they are very careful about not moving objects around, right? So this is pretty robust to changing positions and stuff like that. All right, so now I talked about that we can simulate things and also kind of where we want to go with scaling, using, for example, a teleoperation, task and motion planning to scale up this process. We can also, of course, combine all of this task and motion planning with reinforcement learning, right? Where we say, okay, that certain step is something that I want to learn through reinforcement learning. So that we have kind of a mixture of all these different data sources in simulation. Now, how can we kind of connect that to get this more what we call open world reasoning that, of course, we'd like to have in robotics, meaning dealing with unknown objects that the robot has never seen before, or also using human language to task the robot to do something and understanding that language and then connecting it back to the robotics level. So there's different ways on how we could think about making these connections with these LLMs. By VLMs, I mean these vision language models, very large models like GPT-4o and others that reason both about images, videos, and language. And VLAs is also a word, is a vision language action models. These are these kind of large models that output kind of actions directly that a robot should execute. Okay? So one way to think about this, and there's a lot of work in the community, and we did some work ourselves as well, where you say, well, the input to the system is, for example, some images and text, the text describing what the robot should do. We just take one of these off-the-shelf vision language models, one of the GPTs, for example, and the action model then, for example, generates, for example, Python code. We did some work where it generates Python code that then calls functions that the robot should execute. So, for example, the vision model might identify that the location of the bottle in the image, for example, mask it out, and then call a function in Python that says grab object, and then this function grab objects is one of these robot skills that we have pre-generated that then the robot can execute. So we have a strict separation between, let's say, the reasoning of the vision language models and then the skills that we as roboticists, let's say, have developed, right? And I think you can get actually very successful demos from that and good progress, but I think ultimately we might have to go a bit beyond that, where we're just using these vision language models off the shelf, right? Because they are often not trained on the capabilities that we as roboticists care about, for example, 3D reasoning. An alternative to that is, for example, there's been work on RT2, OpenVLA. Google DeepMind was one of the key drivers behind that, which is just monolithic end-to-end vision language action model, where you say in-come text, images, and possibly the state of the robot, which means the joint encoders of the manipulator, for example. And the vision language action model is actually trained to output in text form not raw commands for the robot, but low-level, joint-level commands for how the robot should move in order to execute that. And they showed some pretty nice capabilities with these, but overall, I think these kind of systems are still extremely data-hungry and also rather brittle, actually, still, if you want to execute them in the real world. So I think where we need to go is somewhere, let's say, in the middle here, where we still have as input these text, images, and robot state, but then we call these vision language action models that don't output immediately, let's say, delta joint commands or something like that, but what they output is some information and this is something we can talk in the Q&A later about, but some information that then drives these lower level, for example, policies, right? So we have this two-layer approach where we have high-level reasoning through vision language models, and then we have the lower level policies that then execute on the real robot. And the key idea is that the vision language models, they don't have to be really good at 3D reasoning possibly, right? But the policies, they need to be good at 3D reasoning because they need to execute in the real world. And the interface between them could be different kinds of things. I want to give you one example of very recent work we've done, let's say, in this direction, just to give you an idea of what I'm actually talking about here, okay? So let's look at this kind of approach a bit more detail, where the idea is, and this work is hamster hierarchical action models for open world robot manipulation, where the idea is what we did is we said on the upper level we used a fine-tuned vision language model, okay? And these vision language models are just like the ones that you know where input is an image and a query about the image and the output is an answer relating to the image, for example. And there's various different open source models nowadays that you can actually download the weights and you can fine-tune them with your own data, right? So that they can maybe improve on a certain task that you like them to become better at. In our case, we used a model that was actually developed by Nvidia, the VILA model. And the output of this model, kind of the interface to the lower level reasoning, in this case was just a 2D trajectory sketch. I'll show you a bit more what that means, okay? And then we have 3D policy that takes as input maybe still image and task, but also the sketch, and that should help the lower level policy to generalize better. Okay? So again, the key trick is that the upper level is mainly trained on 2D images because 2D images are just so abundant, and they have this open world reasoning capabilities that we get with these very large models. And the lower level is more capable in the 3D reasoning domain. And the hope is by combining these two that the lower level model gets also a little bit of this open world reasoning, kind of inherits some of that. Okay? So let's look at the upper level first, how we fine-tune this. So the idea is that we take one of these vision language models, again in this case VILA, and how they all kind of work related is you get as input an image, you tokenize the image, and then you get some query about the image. For example, this is an image of. You take the text tokens, you align them, and then they generate an output, for example, a cat. Okay, the words a cat. Okay, so the input is images and text, and the output is these kind of text tokens. The problem with using these directly for these kind of robot tasks is often that they haven't seen a lot of robot-relevant data, so they are not really good at fine-grained spatial reasoning and things like that. So what we want to do is we want to fine-tune them on tasks that are more relevant. In our case, there's these different kinds of tasks. I'll give you an example for what they look like. But the idea is now we send as input an image for the robot. It could be from a simulated environment. And a task, for example, look at the middle one here. Put the wine bottle in the wine rack. Okay? And the output is text that describes the trajectory the robot should pursue in order to do that task. Okay? So we're still using language output in this case, but the language output is fine-tuned to give us these trajectories. Okay? Let me just show you what data we use. We use actually real robot data for that. This is there's the bridge data and droid data, so there's like 10,000 trajectories, 45,000 trajectories. And it looks like a demonstration video could be something like this. Move the green object in the silver bowl. And we take that video and convert it. We just take the first image and then track the robot arm in the video and generate this trajectory. And that trajectory is the desired output that we want to get from the model. Does that make sense? And I'm just visualizing it here as an overlay on the image for now, but the model itself actually outputs the pixel coordinates, right? And then we can draw it on the image. I'll give you another example. Put the blue Lego in the open drawer and then close the drawer. We take the video and we just track the position of the gripper, and then we get such a trajectory down there. Okay? And we can do this, of course, now in a fully automated way. And now the idea is we can take this vision language model and train it to take as input the image with the task and to generate as output the 2D trajectory of how the gripper should move for that task. Yeah? We can also use some, for example, simulation data. There's data that's called RL bench, is one of these environments. Screw in the rows light bulb, and these are the tasks that are then executed in this benchmark environments. And below you can see kind of the training data we extract for this high-level vision model. So the nice thing for the vision model in this context is it doesn't have to be precise in 3D reasoning, right? It just has to generate kind of this overlay on the image of how the arm should move. Now you can see, for example, on the right side, if slide the bottom drawer open, then it just says, okay, this is where you start. The first circle indicates actually that the gripper should close here, and then these are different points that then generate kind of the trajectory to the end. Okay? And let me just, and we tested the capabilities on this on some human evaluation, and the model performed, not surprisingly, of course, much better than any of the other models that weren't trained specifically on this, even better than GPT-4o and other of these very high quality models. Let me just show you some examples for some kind of generalization we get from this. Of course, we had to do move the block to Shenzhen Huang, and it realized there was some block stacking kind of data that you have to go here, close the gripper, and then move it over there. Okay. Here, this is interesting. So in the training data, these are some examples from the RL benchmark. Here's the screwing a light bulb, and here is, for example, pressing buttons. And these tasks were only present in this simulation data. But then afterwards, because the model was pre-trained on huge amounts of real-world images, it actually transfers pretty well to real-world images then. For example, this is a picture of a real light bulb and the robot there, and then if we say screw the light bulb in the lamp, it can actually predict correctly, okay, you first got to go here, close the gripper, and then move it over to there. So we see some, in this case, sim-to-real transfer that we get automatically through this model. On the right side, here's another example for button pressing, for example. If on the training data, we only had examples like the ones you see on the top. And in the training data also, these buttons were all indicated by red or orange or green or something like that, by their color. But then at test time, when we showed this real image, you can see here, push the button with the color of cucumber, then press the button with color of fire. The model automatically was able to identify, oh, cucumber must be the green one and fire must be the red one, and we're getting that generalization for free because we're leveraging these large-scale models. So this is a kind of generalization that you would just never see from a small data set trained robot model, I would say. One final example that we were actually very surprised about, there were never sketches in the fine-tuning data, but then we just tried, okay, if we give it a sketch like this, right, on the right, place the cup on the cup holder or so, it was actually able to generate trajectories that were very meaningful even for these sketches that had nothing to do with the raw training data that we showed it, right? So again, I'm just showing this to highlight these generalization capabilities at this VLM level here, okay? I guess, yeah, I have like 10 minutes left, so I think I will be able to get through this here. So now that we have the high-level model, we still need a low-level policy that can actually execute some of this, right? And there's different techniques out there, of course, and different ones we tried. There's, for example, these diffusion policies that Guanya also mentioned, right? We use a specific model, RVT2, in this context, and I just want to briefly give you an idea of how this works. But again, the idea now is that this low-level model now gets as input an image from the robot's camera. It gets as input also, let's say, joint encoders and the task in language, but it also, in addition to that, gets a kind of like this trajectory picture, right? So that gives it kind of like guidance that comes from the high-level model, okay? Let me just briefly describe the 3D reasoning, the 3D policy, where we're coming from there. This was the first work that we did, Perceiver Actor, which was also about training 3D robot manipulation tasks from few demonstrations. And we were leveraging transformers for that. And the idea here was actually that if you want the robot, for example, if the task is, for instance, open the middle drawer, then rather than outputting a dense policy of how exactly the arm needs to move, we wanted to train a model that just says, to solve this task, first the robot has to get to the handle of the drawer, for example. So we had these intermediate keyframes of how the robot should move. And then the rest is done by general motion generation, just by motion planning, for example. So the role of the transformer then was to take as input the language, open the middle drawer, and a voxelized, 3D voxelized version of this environment, as you can see here on the left. These are kind of fine-grained 3D voxels. And these were input to the transformer, and the output of the transformer was then, to which of these voxels should the robot move the gripper next in order to solve this task? Okay? And by moving the gripper is both in XYZ, but also the 3D orientation, which we can read out then. If you want details, I'll encourage you to take a look at the paper. This is what this then looks like, for example. Imagine the task is put the tomatoes in the top bin. On the left, you see the camera view, but on the right side, you see this voxelized representation. And this red heat map here, this red dot, that indicates the output of the transformer model as that is where the gripper should go first. Okay? So here's a gripper position now, visualize at the position that the transformer model suggests. And this is, again, this is also in the realm of behavior cloning. There's no reinforcement learning. This is based on prior demonstrations, right? So for example, then it moves down and it also gives the command to close. Now if you look on the left side, the robot executes this. We now feed that back into the transformer and the transformer says, okay, the next goalpost is to retract the gripper up. And then you can see on the right side now, the next one is, okay, we got to move it over. And this can be trained from relatively few demonstrations and also by changing orientations and translations, it becomes actually pretty robust to moving, for example, some of these objects around. Let me just give you an example of here he trained, he took training data that took Mohit, who did this work, less than 3 hours. He generated 53 demonstrations. And then after training, this is what the model then is able to do. So it actually generalizes pretty well to changes in positions and stuff like that. And also importantly, this is a single network transformer that is trained across all of these tasks. So it's not a task-specific network, right? It does all of them. The key limitation of that work, first of all, this work was because it was voxel-based. It's not very efficient, right? Like the reasoning, doing the attention across all these voxels. So we then developed, actually after that, another network structure that's called robotic view transformer, which is based on from projections onto this 3D space, so that actually the transformer only has to reason about 2D. And I think, Bernadette, did you mention that this morning? Yeah. So we're using actually, but just here context. So this is on RL bench success rates, and the perceiver actor that I showed you with this voxelized representation had like 50% success rate, but it only operated like 5 frames a second. And with this RVT2 now, we are at 81% success rate and 20 frames a second. So it just scales faster, it trains faster, and also gives us a better success rate. So we can do actually relatively fine-grained behavior cloning tasks with this, as you can see here. So, but this is the key limitation of this is still, because it's just trained from these few demonstrations, it cannot generalize to new language or new objects or anything like that, right? It's actually just trained on exactly what it has seen and nothing else, right? That is one of the key limitations. But now the idea of this work was, of course, to somehow connect that with this high-level transformer model that I showed you, the vision language model, okay? But so what we did here is just show you experimental setup. What we did, we generated 320 examples of these kind of tasks. So for example, here you can see pick up the energy bar and put it in the red bowl. And on the left, you can see what our high-level trajectory model outputs for that task. Okay, so it needs to identify what object are we talking about, where does it have to go. On the right, you can see, for example, press the right red button. These were, and we generate some demonstration, or push down the drink in that case where it has to topple over an object. Okay, so we generated 320 examples, tasks, and then what we can do is between them we can rearrange objects and we can change the words we're using to describe the task and things like that, right? So let me just show you some results we're getting here. If we evaluate the RVT2, which I just showed you, on these kind of modifications to the tasks in the test scenario, on the left side you see, for example, this is success rate we are getting if we just rearrange these objects relative to each other. It turns out that it kind of overfits to the examples we are giving, and it's not doing as well anymore, okay? Then another thing we can do is, in the test cases, we can just we add other objects to the scene, or we change the color of the table and things like that. And you can see we're getting quite a drop in performance then, right? Again, because the model kind of overfits to the data it has seen in these few demonstrations. But it gets worse as soon as we do anything semantic different to the task. So for example, in the object names, for example, here in the training, we might have said, pick up the Snickers or the candy bar, and then a test we might say, pick up the sweet object and put it into the bowl, right? So of course, the one has no idea what a sweet object is or something like that, right? So it's gonna fail miserably, which means this is kind of more or less like picking one of them randomly, right? Another one we did also is where we then said, pick up the left object and put it in the left bowl. So understanding what left means and right and things like that. Of course, also it hasn't seen that in the training, so it can't do that at all. And on the right side, we even introduced, let's say, a new object that was never seen in training, like the smiley face. And again, RVT has no idea what to do with this, right? This is, if we train, OpenVLA is an end-to-end vision language action model. I briefly mentioned that when I gave you this overview slide, but this is kind of the largest open source model for robot training, and we can fine-tune that model on this data that we generated. Without fine-tuning, it has kind of almost a 0% success rate, so we had to fine-tune it on the data, and here you can see how it behaves on these different modifications, where it's actually also dropping quite a bit in accuracy. And these are the numbers we are now getting with this model that combines this high-level reasoning with this 2D trajectory interface to guide the low-level reasoning. And you can see that the success rates are significantly higher than either the monolithic end-to-end model or the pure low-level model that we had, right? So we're really now seeing this benefit of the semantic generalization and also of combining that with this lower level 3D reasoning. So I think that's kind of a very promising signal that we can see here, right? So as you see here, for example, when you look at these three blocks here, so in this case, we see almost no drop in the performance, even if we use totally different names or we suddenly say the left object and things like that, because the lower level model, the RVT model, learned to interpret that trajectory as a signal like, okay, that's the object I got to pick up, and this is where I have to drop it, independent of the name, right? The naming, that was handled by the higher level model, and it's just being learned from the training data, right? So I think that's very promising. And with that, I'm coming to my final slide. I'm sure Ben is getting nervous already, so, but you're still sitting, so that's a good sign. Just wrap it all up. So I think we've amazing progress in vision language models, and but at the same time we got to be aware a true like RobotGPT moment still is quite a way to go. It's not going to happen, I think, within the next few months, at least. At the same time, I got to be careful here. Yes, I know. Just leveraging these models as they are and say, we'll just deploy them in the robotics context, it gives you a lot of leeway already, but I think ultimately they have a pretty low bar ceiling at what they can achieve, right? We really have to get into the business, I think, where we as roboticists have to help train these models, right, on the kind of tasks and the kind of data that we as roboticists care about, right? And by that, I don't only mean, let's say, generating the data, but also, for example, 3D depth perception, joint encoder information, tactile feedback. All of this needs to be, I think, integrated into these models kind of as a first-class citizen and not just an afterthought, right? So, but I think to do this, it's our duty as a robotics community to help doing this and not just wait for other communities to solve all these tasks for us. I think these open source models and fine-tuning them is a very promising way to go just because of scaling issues. So you don't need thousands of GPUs to do this because these models were already pre-trained on thousands of GPUs and huge amounts of data. What we have seen in the data, in the examples I just showed you, that this also helps to bridge the sim to real gap because you have this mixture of sim data and real data. And overall, I think that simulation can really help us tremendously in this endeavor to train these very large models. And after Karen's talk, I felt bad because usually as roboticists, we always have the advantage that we have some videos to show and stuff like that in images. But Karen's talk was so awesome with all these little babies and little piglets. So I thought I have one little video with that was my daughter at the time. Wait, I'll show you. You might have remembered that. So I was reviewer for Ichkai. I was an area chair, so I had to handle 50 papers. And this is my daughter helping me. So we don't need LLMs for doing the reviews for us. So. There we go. All right. Thank you. Oh, wait. And of course, thanks to all the people who actually did this, right? Like mainly, of course, Nvidia and various people and colleagues also at University of Washington, and all the great interns that we had over the years who really made many of these projects work. Also, of course, Bernadette was one of our interns, so glad to see this. Okay, thank you.
Let me ask the first question, which is, what should we be learning from Karen's talk about the next steps that are going to happen in this world?
Yeah. So, first of all, I totally agree that on the long run, we need to do these much more developmental inspired work. Also, for example, I think Guanya, for example, mentioned that already, that for example, the work I showed here mainly focused on kind of offline learning, right? Like you generate data and then you learn from it and you do some fine-tuning. But I think the next steps will really have to be improving these models and learning better models and new tasks in the wild, in the real world. So I think this is clearly we have to go lifelong learning for all of this because we'll never get there just pre-training these robots to be capable of all these things. What makes me still hopeful, and also where I think like this work, even if on the long run it will be more based on RL and in the real world, I think currently we often put our robots in the real world with zero knowledge, right? We just say, oh, I run my RL algorithm and my robot has to learn everything from scratch. We humans clearly also don't learn everything from scratch, right? So I think these kind of techniques can really elevate the kind of capabilities that we have in our robots such that they can hopefully learn in the real world much better and faster than they do right now. But ultimately, yeah, I totally agree. We have to make also huge progress in these areas of lifelong learning and learning from scratch as well.
Thank you. I think we do have time for another question, or maybe even two. Yes.
Thank you. Great talk. I have a question about the 3D and 2D representation. So the line of perceiver, actor, and RVT seems to suggest that having 3D or multi-view or voxel representation seem to be important for robotics. But then the high-level reasoners seem these days still need their text and 2D images. So how do we bridge the gap between like this 2D to 3D gap in the future? Is there a future where we can have 3D like language model as the high-level reasoner?
Yeah, no, that's a great question. So this is kind of like a little bit of a crutch right now, what we're doing here, right? Where we say we'll leave the higher level to do 2D and then we do 3D only at the lower level. Clearly, even the higher level at some point has to have a much better 3D understanding as well. And right now it's just driven by the fact that we don't have a lot of training data for the 3D layers, right? One way to look at this, or I didn't, because of time I left it out, I have a slide, these multimodal models, for example, that currently there's a whole community, right, like multimodal LLMs, where they take in language and vision and video and, for example, audio. And also they are now multimodal on the output, which means they can now output text or videos and images all with single models, using, for example, ideas of you train for a certain modality, you train these robust, what's called tokenizers, and then you align these tokenizers to your, for example, language reasoning model. And I think one promising idea could be to train very robust tokenizers specifically for 3D reasoning, tokenizers for joint state, for example, tokenizers for touch sensing, train them on very large data, but maybe in a more isolated way, and then map them into this joint token space so that they can communicate with the language model. That is kind of where I think we should go, but it's also just beginning the work we're doing there. Yeah.
One last question.
Awesome. Thank you for the awesome talk. I'm going to ask you, your methods are quite general, but I'm going to ask you to speculate on kind of two problem classes. One is this idea of we would like our robots to really help us maybe change our kids, for example. That's a situation where change your kids' diapers, for example.
Oh.
Like suppose...
Make breakfast or...
No, just like change their diapers. Like say,
change it up. Oh my gosh.
So it's a situation where you get to have lots of video demonstrations, like you can watch other people do it, but you never get to have any experiential like trial and error. You have to one-shot get it right. And another problem class is like changing horseshoes. Like you've seen people like scrape off the nail of the horse.
Oh yeah, these tasks are.
I'm curious how you think your progress in SIM and these RL algorithms and these VLMs, how are they going to try to address these types of problems?
I think, first of all, I mean, the one answer could be simulation is only going to get better too, right? So we will at some point maybe not fill diapers, but deformable things and stuff like that, right? All of this is improving. The visual quality is also improving by using these diffusion capabilities. On the one hand side, simulation will get better, but I think coming to these kind of really complicated tasks, I think it's going to be extremely hard to get there through this. I think that's an area where we clearly will need more real-world learning and training. But I think, as I mentioned, I think at least these kind of techniques and tasks can help the robots to at least have a general good understanding of 3D reasoning, what happens when I move my arms in a certain way, so that the learning of these much more complicated tasks in the real world can be done much faster, because we humans also learn these things actually surprisingly quickly, as you know.
Thank you very much.
Thank you.
Let's give him another round of applause.